to this very interesting conference webinar. My today's talk is going to be about my efforts trying to elucidate the reaction mechanism of ammonia synthesis on a metal nitride, cobalt molybdenum nitride. And this was research that I mostly done while I was at University College London. But I continue this research on other materials at the moment at the university where I am now, which is the University of East London. So just a few things about ammonia. Ammonia is used in fertilizers. As you know, it's used in the form of ammonium nitrates or ammonium phosphates. And it is the preferred nitrogen-containing nutrient for plant growth. So plants use ammonia to grow. So 50% of the globally used ammonia is synthesized industrially via the Haber-Bosch process, which is a process that has been developed for more than 100 years and is very well established. And the other 50% is produced by nature by nitrogenases, which are these metalloenzymes, and this is the natural way of producing ammonia. However, as the population grows, we need to industrially produce more and more ammonia, and therefore it's good to find ways to produce it at a lower energy cost, because 2% of the global energy supply is used actually for this Haber-Bosch process in the synthesis of ammonia. So it's quite important to find new catalysts or new pathways in which we can produce it at a lower energy cost. So what is ammonia synthesis? Basically, it is the reaction between hydrogen and nitrogen. Hydrogen are these diatomic molecules. Nitrogen are also diatomic. Nitrogen has a triple bond. Hydrogen has a single bond. And you need to break these single and triple bonds in order to form 6 NH bonds, which are found in ammonia. And there are catalysts that can do that, but it requires high energies and high temperatures to do this. And therefore, the cost for the production of ammonia is quite high. So first, we wanted to see, can we model the reaction mechanism using without a catalyst? Just in gas phase. How much energy is it needed for nitrogen and hydrogen to react in order to produce ammonia? And you can see in this potential energy diagram here, we start with nitrogen, and there is the first hydrogenation barrier is 729 kilojoule per mole. So that's definitely a reaction barrier that could be helped by the use of a catalyst. The second hydrogenation barrier is barrierless, and that's because of the formation of this hydrazine intermediate. And then third hydrogenation step is again very high, 658 kilojoule per mole. And therefore, we definitely know from these Gibbs free energy calculations that we need a catalyst for the reaction to happen. The barriers are quite high. So the Haber-Bosch process was first was studied very much by Ertl and his co-workers, and they found that this is a Langmuir-Hinscher mechanism in which you have the absorption of nitrogen, the absorption of hydrogen onto the surface. The hydrogen dissociates, forming atomic hydrogen. The nitrogen dissociates, forming atomic nitrogen, and then the nitrogen recombines with the hydrogen, forming first NH, then NH2, and then NH3. And this reaction mechanism is well established. for the iron catalyst, which is the industrially used catalyst for ammonia synthesis. And the question is other mechanisms that we can produce ammonia. So it's very important to acknowledge that the reaction mechanism of ammonia synthesis is exothermic. Therefore, low temperature will shift the reaction towards the product. However, if the reaction is too low, then the rate of the reaction is not high, and therefore what you need actually is moderate temperatures. Also, you have 4 moles of gases, 1 mole of Na2 and 3 moles of H2, going to 2 moles of ammonia. Therefore, according to Le Chatelier's principle, increase of the pressure would shift the reaction towards the product. So in fact, the iron, which is iron potassium oxide promoter catalyst, which is used industrially for large-scale ammonia synthesis, uses temperatures between 400 and 500 degrees Celsius and pressures between 100 and 200 atmospheres. So, so our task was to find a catalyst that could work at lower temperatures and therefore save energy. So how do you, this is quite difficult to do actually, because the ammonia has a triple bond, which has a bond dissociation enthalpy of 942 kilojoule per mole. So you need to find a catalyst that can activate or dissociate this bond efficiently, and that's quite hard actually. But cobalt molybdenum nitride, which is the material that we studied the reaction mechanism on, is actually more active than the iron catalyst, but it's currently not used in the industry. But it's interesting to know that the ruthenium, there is also a ruthenium graphite catalyst, which uses ruthenium that is supported on graphite. That was first computationally studied by the Norskov group and who, and then afterwards it was people started to use it in the industry for small for ammonia synthesis. So that in that mechanism, they found that it's a Langmuir-Hinshelwood mechanism, and in which you have the absorption of nitrogen, the dissociation of nitrogen, the absorption of hydrogen, dissociation of hydrogen, and then the formation of NH, NH2, NH3, and then ammonia. And they found that this, the rate determining step in this mechanism was actually the dissociation of nitrogen, which happens more readily at steps rather than terraces. So if you had a step, that would actually increase the rate of the reaction quite substantially. We had some experimental evidence from isotopically labeled nitrogen experiments done from our collaborator, Justin Hargreaves at the University of Glasgow. And they basically found that we need to consider a mechanism in which the nitrogen does not dissociate. So there should be an associative mechanism. So our first idea was then to design a reaction mechanism in which you don't have the dissociation of nitrogen. And you can see here, if you have a nitrogen vacancy, which is just a missing nitrogen atom on the surface of this catalyst, then the nitrogen can absorb end onto that nitrogen vacancy, and it can then react with hydrogen coming from the gas phase, forming this intermediate, this hydrazine intermediate, which then further hydrogenates to form a diazine, which decomposes to produce ammonia, and leaves the nitride on the surface. The nitrogen then further hydrogenates to form NH, then NH2, and then NH3, and then the catalytic site is emptied again, and it's ready to take the next nitrogen molecule. So It's a full catalytic cycle. And the idea was that the nitrogen does not dissociate, but it becomes hydrogenated, and therefore weakening the nitrogen-nitrogen bond this way. So we took the bulk crystal structure of cobalt molybdenum nitride, which is actually a very interesting material. You have these cobalt clusters, cobalt 8 clusters, which are in a hexagonal array, and they are embedded into this molybdenum nitride framework. And you have the highest density of these cobalt clusters along the 111 surface. So we then decided to just look at the 111 surface of this catalyst, but we found that there are different surface terminations that this material can have, and therefore we made models, slab models, which are shown in this picture here, in which you had a slab of the surface, and then a vacuum gap from which you would approach the gas phase molecules to the surface and react them on the surface, computationally, all of this. And these are the surface terminations that we had. There are some surface terminations that did not have any nitrogen on them. For example, in this A and D surface, the nitrogen is subsurface. There are some surfaces that have 5-volt nitrogen, which is a nitrogen that has 5 bonds to the surface. And there are surfaces like C here, which has nitrogen forming 3 bonds with the surface. And we made some calculations, and we found that the surface C can have the highest density of these nitrogen vacancies. It has these 3-fold. You can see that the nitrogen is quite dense on the surface of this material, and the barrier for its removal was not that big. So this is shown in this vacancy concentration diagram as a function of the temperature, where you can see that in the temperature range that we were interested in, which was between 400 and 600 Kelvin, the surface C had the highest density of these nitrogen vacancies. So we then took this surface and we adsorbed nitrogen to the surface at all the symmetry unique positions. So it was a quite big unit cell that we had modeled, and this resulted in 8 sites in which at which nitrogen could adsorb, and only some of these sites it would become activated. So at site 2, it would become activated in an end-on configuration, which was when it adsorbed onto a nitrogen vacancy or the molybdenum nitride framework. And at site 8, it would become activated in a side-on configuration, and that was a surface cavity. So you had two positions at which you had activation of the nitrogen bond, and we thought that this is important in the mechanism because that indicates significant weakening of the nitrogen-nitrogen bond, and therefore the mechanism should proceed following this pathway, in which these are some intermediates of that pathway. So in these studies of the adsorption of nitrogen on the cobalt molybdenum nitride surface, we found also another new type of adsorbed nitrogen, which is the tilt end-on adsorbed nitrogen, which is this structure here, which is a structure where it's simultaneously bound to molybdenum and the cobalt atom. And that was published in the Journal of Physical Chemistry. So we explained this new adsorbed configuration using molecular orbitals, the frontier orbitals. So if you and these calculations were done using Laplacian perturbation theory, using correlation consistent polarized valence triple zeta basis set. And this end-on configuration was basically due to the donation of d electron density into the empty LUMO orbital of the nitrogen. The side-on adsorption is due to these are filled orbitals, so this is due to a donation of electron density from this filled orbital into the empty d orbitals of the cobalt. And the tilt and on configuration was due to the simultaneous donation of electron density from the HOMO orbital into the molybdenum atom, into the cobalt atom, and the HOMO -1 orbital, which is like a sigma orbital, that was donating electron density into the cobalt. So I'm sorry. So the HOMO -1 was donating electron density into the cobalt, whereas the HOMO orbital donates electron density into the molybdenum. So that explained this new adsorb configuration, and we were happy to publish that in that paper in JPhysChem. So then we studied the adsorption of hydrogen on the different symmetry unique positions of this unit cell. And we found that there are 8 positions that hydrogen can bind. And in some of these positions, it will bind in a dissociative way. And in other positions, it will bind molecularly. So, hydrogen chemisorbs dissociatively, mostly on the cobalt-8 clusters. So that makes sense because it's a transition metal. So hydrogen likes to dissociatively absorb on these cobalt clusters. And the hydrogen would absorb chemisorbed molecularly on the molybdenum nitride framework, which was sites 1, 3, 4, 5, and 8. So using this knowledge of these two adsorbed structures, the molecular and the dissociative form of hydrogen on this catalyst, we then were able to design the complete Langmuir-Hinshelwood mechanism for the reaction, which is shown in this picture here. Basically, just to go through this diagram a little bit, you have the adsorption of nitrogen, the dissociation of it. Then hydrogen adsorbs dissociatively on the cobalt-8 cluster. Then hydrogen transfers to nitrogen atom, forming this amine intermediate. Then the hydrogen, another hydrogen adsorbs to the nitrogen, forming this azane intermediate. And then finally, a third hydrogen transfers to the nitrogen, forming NH3, which then produces the first stoichiometric ammonia, which is dissolved from the surface. And then the hydrogen further adsorbs to the reacts with the nitrogen nitride that is present on the surface, producing NH first, then NH2, then NH3, which also dissolves from the surface, freeing up the catalytic site. So this was the Langmuir-Hinshelwood mechanism, which is the one that is currently known to be happening for iron, for the iron catalyst. But of course, in our case, we have also looked at the Mars-Van Crevelen mechanism, in which you have the adsorption of nitrogen, then in an end-on configuration, then the reaction of hydrogen with that, forming hydrazine. Then hydrogen molecularly adsorbs to the cluster, to the molybdenum cluster, and transfers a hydrogen, forming this diazine intermediate that readily dissociates, forming a tertiary amine and dissolving ammonia. Then this azane intermediate reacts with hydrogen, with molecularly adsorbed hydrogen on the molybdenum cluster, forming NH2, then NH3, which then desorbs. And so you can see that this mechanism is actually a little bit, has fewer steps. And when we looked at the activation barriers for the elementary steps, we were very surprised to see that the LA radial mechanism, which is shown in black in this curve here, has lower barriers for the hydrogenation steps than the Langmuir-Hinshelwood mechanism. So therefore, we concluded that the ammonia synthesis mechanism might actually be happening through a different mechanism on cobalt molybdenum nitride. And since the Langmuir-Hinshelwood mechanism is happening at a certain temperature, we would expect that this new mechanism is happening at a lower temperature. So we think that if we have a way of increasing the number of nitrogen vacancies in cobalt molybdenum nitride, we will able to produce the ammonia at lower temperatures. So with that, I'd like to acknowledge the collaborators of this project, Richard Catlow, Justin Hargreaves, and Said Laziri, who's now in Morocco, and the funding from the EPSRC, first principles design of a novel ammonia synthesis catalyst, and the computational resources from UCL Grace and the Archer. And if you'd like to further read about these papers, please go ahead to these two articles in the Journal of Physical Chemistry. These are the cover images from these articles, and I'm happy to answer any questions.